So on to question 2. So we here have a student studying the reaction between um, sodium HCl3 and HC2H3O2. And then we are given this reaction. They give us the amount in grams and the amount, like the volume of the other aqueous solution. And the student observed bubbles, and the flask gets cooler as the reaction proceeds. So we know that an actual chemical reaction is taking place. So for question A, they asked us to identify the type of reaction. Is this acid base? Is it precipitation or redox? See right here. Well, immediately off the bat, is not a precipitation reaction because in our product side, all of our products, they're either an aqueous, a liquid, or a gas. Since no solid was formed in this reaction, it is not a precipitate reaction. However, for the next one, they asked us, is this acid-base or redox reaction? Now, for those, now obviously I don't remember my oxidation rules. I don't remember all of them. I only remember the ones pertaining to metal. But looking at from here, it doesn't appear as if an oxidation change in the numbers have occurred, Now, I think that's an acid-base reaction simply because, in our reactant side, we have here an acid. We have HC2H3O2, and when we go into our product side, what ends up happening is that hmm, a double replacement occurs. So the sodium and the hydrogen, they do a double replacement with each other. So on the product side, we have Na where H was originally, and that hydrogen, it goes, when the hydrogen switches with the sodium and binds to HCO3, we get the formation of H2O and CO2. Now, this isn't just a normal double replacement. This double replacement involved the transferring of, of an H plus ion or a hydronium ion. A proton was donated in this process. So for this one, it is acid base. Acid base because, well, an H plus proton was donated. It was donated from the HC2H3O2 to the HCO3 ion, and it gave us H2O and CO2. I think you can argue that H2O would be the conjugate base of it. So, well, from H3 to the HCO3 ion. Okay, so that would be part A. For part B of number 2, they asked us here, based on your information, we need to identify our limiting reagent. So now for the limiting, we need to find the smaller mole amount. Here they give us our amounts, so they give us 2.24 grams of our solid and 60 milliliters of 0.875 molarity or molar of our acid. Now, first thing first, when in doubt, convert everything to moles. That's what we're gonna do. So we're gonna first convert our 0.875 molarity. So molarity is moles per liter. So moles of acid per liter, and we're gonna multiply it by 0.06 liter because milliliter when divided by 1,000 we're going to get 0.06. So units cancel and we're going to be left with 0.0525 of our acid. And obviously that's going to be in moles because that's the only thing that isn't cancel. So moles. For the next one, what we're going to do is we're going to do the same thing but this time with our metal, or not our metal, our solid. So we have 2.24 grams. For every mole of that compound, the molar mass is 84 grams. That's going to go 0.0266. Well, that's going to go 0.266 moles of NaHCO3. Now, normally we'll have to do an actual stoichiometric calculation, but because there is a 1-to-1 ratio, we don't necessarily need to do any further stoichiometry. At this point, we can compare because their ratios are equal to each other. So, based off numbers, 0.0266 is less than 0.0525. So, NaHCO3 is our limiting. So, for part C, the student observes the bubbling. They notice rapid bubbling in the beginning of the reaction, but as the time passes by, the bubbling starts to slow down. And we need to explain this change in the reaction rate in terms of collision between in terms of the reaction particles. So for this one, we need to trace back to now in a reaction, we know that a reactant is going to be used up. Okay, as our reactant is used up, our products are going to form. Now, how the reactant used up can be in different ways. So, for one thing, it can be in terms of amounts, or it can be also in terms of concentration, like for an aqueous solution, since concentration also determines the rate of a reaction. So in this case, since we both have a solid and an aqueous solution, we're going to say that as the reaction goes on, the amount of reactant decreases from consumption. And because we are losing the amount of reactants, we're losing concentration. The frequency of the collision between the molecules are going to happen less frequently. Therefore, there is a decrease in the amount of collisions because well, because the reaction rate is decreasing. So remember that as a reaction rate decreases, the reaction starts to slow down. A very large reaction rate means that your reaction would be near instantaneous. So if the bubbling is happening less and less over time, then the reaction is decreasing, the reaction rate. So for the next one, for this one, part D, this one's thermodynamics. I'm not sure about thermodynamics. I don't know how to answer this one. But judging from how part 2 was asking, I would say that this would be entropy driving the force of the reaction. I'm not sure why. I don't know if it's reading that so much, but it is entropy. Okay, so for part E, the H2O3 ion has 3 carbon to oxygen bonds. 2 of them are the same bond length, and the third one is longer than the other 2. So we need to draw a diagram, a Lewis dot diagram, or diagrams for the HCO3 that are consistent with the given information. Now this depends on how well you're familiar with Lewis dot structures of polyatomic ions, but from what I know that in past experience that HCO3 has a resonance structure. So there's 2 variations of the Lewis dot diagram for it, and that we need to draw. So following in with our diagram, the hydrogen always needs to be in the outlier. You have an oxygen, a carbon, and 2 oxygens at the bottom. Now, if we follow our NOS calculations, we would be basically getting here are NOS calculations. We need 34 electrons. We only have 24 electrons available because of the period number, so we only have 24 valence electrons present. And when we subtract these 2 values and divide by 2, we should be getting 5 bonds present. So 5 bonds present. So first thing first, we draw our bonds. 1, 2, 3, 4. Carbon is that atom, the central atom. It can't just have 3 bonds. It needs to have that complete octet because carbon is so perfect. So we're gonna have to draw a double bond for this one. This is gonna give us like the remaining lone pairs, and we just fill those out. So this is our lone pair. For this one, for this oxygen at the top, it's gonna have 2 lone pairs, and hydrogen never has a lone pair. Now, since this is an ion, we need to draw brackets. Brackets are important. And we need to draw its negative sign since this is a negatively charged polyatomic ion. We're going to draw a resonance arrow because what the resonance arrow tells us is that there's more than one way to draw this Lewis dot structure. So for this one, again with the oxygen, carbons here, this oxygen on the left side can have a double bond, while this one can have a single bond. So we can just flip it. And again, we do the negative sign. So that's how you'll draw your Lewis dot structure for HCO3. Yeah, okay. So for the next one, we have here for part 2F. So student prepares an amount of our reactants. The pH is measured to be 4.7. Student adds 2 drops of HNO3, stirs the sample. The pH remains at 7. We need to write a balanced net ionic equation for the reaction between HNO3 and the chemical species in the sample that's responsible for the pH remaining. Well, for the species responsible for remaining at 4.7. So for this one, well, one thing I can tell you is that a pH value of 4.7 means that the solution is an acid. So out of those two, HC2, HC2H3O2 and NaC2H3O2, out of those two, I believe that it is going to be HC2H3O2 that will be our acid. And I think since that one's an acid, it's gonna cause the pH value of that solution to stay the same. For the net ionic equation, just means that we only need to write the equation for the solutions that are present and active in the reaction. For this one, is acids are aqueous by nature, or acids are solutions. So HC2H3O2. It's going to be, we can just separate them. So H plus C2H3O2. And since we gave up a positively charged proton, this charge must be negative. And it has to react to H, C2H3O2. Now that should be our net ionic equation. Between HO3. Okay. For the next part, they're asking us, oh wait, for number 6, part A, we have here a chemical equation that's in equilibrium, or that's admitted to be part of equilibrium. So, number 6. And what's happening is that we need to consider the value for K. So our equilibrium constant is 7.7 times 10 to the 7th power. That's very large. We need to determine the concentration of our basically our product in the 10 milliliter solution, and we need to adjust by proportions. So here's what we do. We do know that we have 50 milliliter of a solution for both reactants. So both reactants are 50 milliliters each. EDTA has a molarity of 0.3 and it's mixed with barium, I don't know how to say that, barium nitrate or nitrite. It's BaNO3 and it has a molarity of 0.2 molar. And it's to produce 100 milliliter of solution. So here's what we're gonna end up doing. So we write our reaction. So we're gonna do our handy dandy rice table. So Ba2 plus the aqueous solution plus EDTA 4 minus, and this is also aqueous and is at equilibrium with Ba EDTA 2 minus. So for this one. Now before we do anything with our rice table, we need to convert our amounts into moles. So for this one, so Ba for the barium ion, so we have 0.50 liters and 0.30 moles. So since our molarity is basically 0.030 moles per liter, our liters cancel out and we are left with 0.010 moles of, oh, I'm sorry, 20. Since our molarity for the barium for the Ba2 plus ion is moles per liter, so we're going to be left with 0.010 moles of Ba2 plus. When we do the math here for the EDTA, we're going to have 0.015 moles of EDTA or minus. Now already, since this is a 1-to-1 ratio, we can already establish that the barium ion is going to be the limiting reactant. Now they ask us we need to find the concentration of our product in the 100 milliliter solution. So now that we converted everything, what we have so far, into moles, we need to convert it back into molarity, but this time it's going to be in terms of 100, or no, it's going to be in terms of 100 milliliter. So we're going to convert back to molarity in respect to the entire container as a whole. So 100 milliliters will divide by 1,000 is 0.1. So 0.010 divided by 0.1. When we divide it all by our milliliters, we're basically going to have a molarity of 0.1 molar of Ba2 plus. And as for EDTA for minus, that one, it's going to be 0.15 molar. So now we're going to actually do our race table. So for our race table, our molarities is going to be the initial. Now, since this is before the reaction, the product hasn't existed yet, so 0 molar. We can already establish stoichiometric coefficients, but also understand that because our K value, the equilibrium constant is so big, and again, let's look that again, like 7.7 times 10 to the 7th power, that's like millions. It's in the millions, I believe. Since our equilibrium amount is so big, we just have to establish that our reaction goes completely in the forward direction, meaning that our reactants are completely consumed. So for our change, since we have such a high equilibrium constant, our molarity of Ba2 plus ion is going to be gone. But since this is also our limiting reactant, then the reaction only stops when one of them goes out. So as for our EDTA is going to be left in excess. This is going to be our excess right here. And since as we continue on with our stoichiometry, the concentration here for the Ba EDTA2 minus is going to gain 0.1 molar. So plus, which means that at equilibrium, this is going to be 0. This is going to be 0.05 in excess, of course. And this is going to be 0.1 molar. So therefore, the concentration concentration of our Ba EDTA2 minus is going to be 0.10 molar, since K is so much greater than 1, reaction gets completely, or goes in the forward direction. In the forward direction. Alright, so that would be part A. Yeah, so this part A is quite a handful, but this is how equilibrium is. So for number 6, part B. 6B. we were asked this question about which which is basically the Shapley principle kind of question. So the solution has been diluted with water for a total volume of 1 liter. So already we need to know solution has been diluted, so the volume has been increased. After equilibrium has been reestablished, is the number of moles of the barium ion present in solution greater, less than, or equal to the number of moles of barium ion present in the original solution before it was diluted? And we need to justify our answer. So basically, is our amount of Ba2 plus ions in this after the dilution has occurred, is it going to be greater than the original, less than, or no change? So here's what we need to know. So because we have diluted our solution, it's from our reaction we know that our product was an aqueous. If we trace it back to solubility, we would know that adding water adding more water to a solution can sometimes allow for solubility to occur. With respect to aqueous solutions, I'm going to say that the Ba2 plus would increase. This all goes back to equilibrium solubility. So it would increase because by adding more water to Ba EDTA Ba EDTA EDTA 2 minus the compound is going to dissociate or dissolve more into their respective ions. So, and that's what happens in solubility. When you add more water, it allows for the solution to become more soluble, or it allows for dissociation to happen more frequently. So dissociate more, producing more barium ion as a result. Okay. Now on to our last question. Question 7. So here we're gonna do. Let's do. Okay, so for question 7a, so a student is given a 25 ml sample solution with unknown monoprotic acid and asked to determine the concentration of the acid by titration. Okay, so this is a titration problem. Now, I know that we haven't gone over that in class so much, but I do know from my own research that titration is just used to solve for the the unknown concentration of the substance. So essentially in titration, you're going to be doing the M1V1 equals to M2V2 kind of equation, or At least that's going to be generally expected. So they're giving us a diagram. So we have two graduated cylinder, and the image shows that one is before titration occurs, and then there's one after the titration has occurred. Now, what should the student follow or record the volume of NaOH delivered to the flask? Now, let's see right here. So here we have, let's see. Well, the most that we can do when asked for what should the student record as our volume, most we can do is to final amount minus the initial amount, and that can give us a volume. So over here, our final amount is at the past the 37 mark, and there's 1, 2, 3, 4, 5, 6, 7. There's like 9 tick lines. So this one's going to be 37.30 ml. And another reason why I'm going to be using the white part of the graduated solution is because the one thing that remained constant was our 25 milliliter sample solution. And the one thing that the student was changing was the amount in milliliters of our base. Since this is monoprotic acid, it just means that our acid is going to be a Bronson laureate acid, so it's going to donate a hydronium ion. So in the before burette, we see that we have an amount of 5 point, and if you eyeball this, like between 5.6 and 5.7. So let's just say 5.65 milliliters. And it's just simple as 1, 2, 3. So final amount minus the initial amount. So 37.30 milliliters minus 5.65 milliliters. Well, just eyeballing, so question mark. So 31.65 milliliters should be the amount that the student is recording. Now then, for the next one. Based on the given information in your answer part A, determine the value of the concentration of the acid that should be recorded in the student's lab. So this is part where I know for sure we're going to be doing an M1V1 equals M2V2 kind of equation, and here's why. So we're going to do here's what I know. Here's what we were given. We were given the volume of NaOH. NaOH. We were given its molarity of NaOH. And we were given the volume of the acid. The acid could be on the what it is. Presumably it could be an HCl acid. Okay. And our unknown, they want us to find the molarity of our acid. So the equation, since we have two separate volumes and we have a molarity of one of them, we can easily find the molarity of the first one. So this can be a simple dilution and concentration equation. So M1 times V1 is equal to M2 times V2. by the laws of algebra. We can rearrange this to solve for m1, and we can get m2 times v2 divided by v1 is going to give us the molarity of our unknown. Let me just assign my variables. Good. So it's already been given that our molarity for NaOH was 0.11 0 molar. The volume of our sodium hydroxide, it was 0.03165 liters, and again I just converted my milliliters to liters. Volume is always be in liters when you do your calculations unless given otherwise. And we know that the volume of our acid, sorry, it's 25 milliliters or 0.025. Is it 0.025 liters?